Good day to you, Professor. My name is Lai Tong Chong, and today I'll be presenting about one of the problem statement that my group is solving, which is transient heat dissipation analysis by using parabolic PDE to design cooling system. So, in order to keep electronic components from overheating, heat sinks are essential for dispersing thermal energy. So, to analyze the heat distribution and also the dispersion of the heat thermal energy, we'll be using parabolic PDE methods such as implicit, explicit, and also Crank-Nicolson method. And these three methods are used because the heat conduction equation is more suitable to create a dynamic model to simulate the heat sink's time-dependent temperature distribution. And throughout the slide, I have already written how the method is used and also how it is derived. So I'll proceed to the programming part, the coding part. So for this situation, we'll assume the heatsink to be a copper heatsink of 0.3 meter thickness. So all the parameter and the values for implicit, explicit, and also Crank-Nicolson method is listed here and here. All these values are used from copper, the copper's material properties. And so for the explicit scheme method coding part, from line 1 until 10, it prompts the users to enter all the parameters such as length, thickness, length or thickness of the analyzed material, and also K, the thermal conductivity, density, specific capacity, and so on. And from line 12 until 17, it does the final calculation of the thermal diffusivity, spatial step size, and also stability limit for the explicit scheme. So from 19 until 23, line 23, it calculates whether the lambda is more than 0.5 because the solution may be inaccurate if it is more than 0.5. So from line 25 until 30, it initializes the spatial and also the temperature grid setup. And from line 32 until 37, it performs the explicit time stepping using the finite difference approximation. And from line 39 until line 52, it plots the temperature versus position graph at the selected time steps. And from line 55 until 58, it displays the final temperature table. So for the programming with implicit scheme method, line 1 and 10 until 10, similarly, it prompts the users to enter all the parameters. And also from line until 2 until 16, it is also similar, final calculation of all the entered parameters. And then line 20 until 25, it is also is the initialization of the spatial and temperature grid as well. And from line 27 until 30, I've built a coefficient matrix used to solve the implicit system. For this one, it's only one matrix. For the Crank-Nicolson, will be two matrices. Line 32 until 40, time stepping loop for the implicit method. And line 42 until line 55. Similarly, it will be used to plot the temperature versus time graph. And from line 57 until 60, it displays the final temperature table. So the programming with Crank-Nicolson method, from line 7 until 14, similarly, enter the parameters. 16 until 19 is final calculation for parameter. 21 until 24, it prints and checks the R value. It's not a strict limit in Crank-Nicolson method, but it gives insight into resolution and accuracy. From line 26 until 32, user manually inputs all the initial temperature at each internal node. Depends how many nodes the user uses. So this one, it can be varied throughout the nodes. From line 40 until 42, here it constructs matrix A and also matrix B. Matrix B is 44 until 46. Yes, all of these are matrix A and B to calculate the implicit implicit half of the Crank-Nicolson. From line 52 until 64, it is the time stepping loop. It prelocates a matrix T_all here to store temperature at each position for all the time steps. It sets the initial condition as the first column. So from line 66 until 75, it plots the initial temperature profile and also final temperature profile after the simulation. And line 77 until 80, it displays the final temperature table. So this is the result obtained for explicit method, and also Crank-Nicolson method. The graph the gradient of the curve slowly decreases as it reaches its thermal equilibrium for the heat sink as the time step increases. Similarly for explicit scheme and also Crank-Nicolson. So this is the value obtained from the calculation in MATLAB. As we can see here, the difference throughout the three methods is negligible, very close together. So after determining the temperature distribution of the heatsink, us engineers can use it to determine the cooling power required for the heatsink to maintain the heatsink or whichever medium used for cooling at a stable temperature. It also can help us to choose the right material and design based on the thermal conductivity to save material costs also. So with that, thank you, doctor, for listening to me, and that'll be all for my presentation. Thank you.